We have learnt that chemistry deals with matter. And matter is made up of atoms and molecules which have extremely low masses and are present in very large numbers. Thus, chemists have to deal not only with a large number of atoms and molecules, but also with calculations containing large numbers. For example, Avogadro number is such a big number that there are 20 zeros after 6022. It is not only inconvenient to write such a large number, but also difficult to perform mathematical operations like addition, subtraction, multiplication, or division with such a number. To overcome this problem, chemists started writing large numbers using scientific notation, also known as exponential notation. In scientific notation, any number can be represented as n multiplied by 10 to the power of n, where lowercase n is an exponent having positive or negative values, and uppercase n is a coefficient that can vary between 1 and 10. Thus, we can write Avogadro number in the exponential form as 6.022 multiplied by 10 raised to the power of 23. Similarly, the number 0.049360 is written as 4.93604 multiplied by 10 raised to the power of -2. Here, we have to move the decimal point 2 places to the right. Hence, we can say that the exponent is -2 and the coefficient is 4.93604. Now let's see how to perform mathematical calculations on numbers written in scientific notation. Let's start with addition and subtraction. If we have to add or subtract any number expressed in scientific notations, we must first check if the exponent of the numbers is the same. Only if they are same, we can add or subtract the coefficients. For example, in this equation, one exponent is 4 and the other is 3. Therefore, in order to add the numbers, first we have to make the exponents same. As 6.62 has the larger exponent, that is, 4, we have to convert the exponent of 4.31 to match the larger exponent. So, we rewrite 4.31 multiplied by 10 raised to 3 as 0.431 multiplied by 10 raised to 4. Now, after taking the exponential factor in common, we add both the coefficients and obtain the result as 7.051 multiplied by 10 raised to the power of 4. The same rule applies to subtraction. The example shown here illustrates the steps to subtract two numbers. Now let's see how to multiply and divide numbers written in scientific notations. To multiply two numbers, first we add the exponents and then multiply the coefficients. For example, to multiply 2.4 multiplied by 10 raised to the power of 3 with 5.6 multiplied by 10 raised to 4. First, add the exponents and then multiply the coefficients as shown. To divide two numbers, first subtract the exponents and then divide the coefficients. Here's an illustration of dividing numbers written in scientific notations. When performing experiments, we often perform mathematical calculations on quantitative measurements to obtain accurate results. People often use the terms accuracy and precision interchangeably. But are accuracy and precision the same? Let's see. If we have few grains of rice scattered in the plate, we can easily count them and say that they are 20 in number. However, what if we were asked to count the rice grains in this bowl? We would count them, but due to the large quantity, we may not be able to confirm if our count is accurate. One way of ascertaining the accuracy of measurement is to repeat it. Let's assume that we know that there are 105 grains in the bowl. Thus, the correct value of measurement is 105. Now, let's say we ask 4 people to count the grains, each 5 times. Shown here is the data of each person. We know that the correct value is 105. If the average value of one of the measurements is close to the correct value, then that measurement is said to be accurate. If the values of measurements are close to each other, and hence close to their average value, then the measurement is said to be precise. Let's look at the data to understand what it shows us. For person A, the average value matches the correct value. Also, the values of different measurements are close to each other. Hence, we can say that A's data is accurate and precise. For person B, the average value is not close to the correct value, but the values of different measurements are close to each other. Hence, B's data is not accurate, but it is precise. For person C, the average value matches the correct value, but there is a variation between the values of different measurements. So, C's data is accurate but not precise. Note that accuracy without precision could be a matter of chance. For person D, the average value does not match the correct value. Neither are the values of different measurements close to each other. So, D's data is neither accurate nor precise. The certainty and uncertainty in a measurement is indicated through the use of significant figures. Significant figure is the total number of certain digits in a number, including the last digit whose value is uncertain. The uncertainty is indicated by writing the certain digits and the last uncertain digit. For example, if a measurement is reported as 16.3 ml, we can say that the 16 is certain and 3 is uncertain, and the uncertainty would be plus or minus 1 in the last digit. Let's see the rules to determine the number of significant figures in a reported quantity. The first rule says that all non-zero digits are significant. For example, 897 has 3 significant figures. 0.23 has 2 significant figures, and 9.87 has 3 significant figures. According to the second rule, zeros preceding the first non-zero number are not significant. Such zeros indicates the position of decimal point. For example, 0.0325 contains 3 significant figures. The third rule is zeros between 2 non-zero digits are significant. For example, 5.01 contains 3 significant figures. The fourth rule is all zeros placed at the end or to the right of a number are significant, provided they are on the right side of the decimal point. Therefore, 0.400 has 3 significant figures. However, terminal zeros are not significant if there is no decimal point. For example, 100 has only 1 significant figure. The fifth rule says that the exact numbers or numbers that are obtained by counting rather than measuring are assumed to have infinite significant figures. For example, 8 apples have infinite significant figures, as 8 is an exact number and can be represented by writing infinite number of zeros after placing a decimal, that is 8.000000 infinitum. Now let's see how to determine significant figures in the results of mathematical calculations. While adding and subtracting numbers, the result should have the same number of digits to the right of the decimal places as the original numbers have. For example, if we add 16.25, 22.0 and 2.062, we get 40.312. Here, as 22.0 has only 1 digit after the decimal point, the result should be reported only up to 1 digit after the decimal point, which is 40.3. While multiplying, the result must be reported with same number of significant figures as there are in the measurement with few significant figures. For example, if we multiply 12.984 by 2.5, the result is 32.46, which should be rounded off to 32, as the number 2.5 has only 2 significant figures. Similarly, if we divide 5.7634 by 1.28, the result is 4.5027. According to the rule, the result must be reported with 3 significant figures. Thus, the correct answer is 4.50. Now let's look at the rules for rounding off significant figures. The first rule is, if the last digit is greater than 5, then the preceding number is increased by 1. For example, in 1.347, if 7 has to be dropped, then the number is rounded off to 1.35. The second rule is, if the last digit to be removed is less than 5, then the preceding is not changed. For example, in 5.332, if 2 is to be dropped, then the result is rounded off to 5.33. The third rule is, if the last digit to be removed is equal to 5, then the preceding number is left as is, if it is even, else it is increased by 1. For example, if 7.45 is to be rounded off by removing 5, then it is rounded off to 7.4. However, if 7.35 is to be rounded off, then we have to increase 3 to 4, giving 7.4 as the result. When we perform mathematical calculations, sometimes we need to convert units from one system to another. This can be achieved through a method called factor label or unit factor method or dimensional analysis. Let's understand this through an example. Assume that we have to convert the length of the object from inches to centimeter. We know that 1 inch is equal to 2.54 centimeters. We can write the equation as 1 equals 1 inch divided by 2.54 centimeters or 1 equals 2.54 centimeters divided by 1 inch. The quantities 1 inch divided by 2.54 centimeters and 2.54 centimeters divided by 1 inch are known as unit conversion factors because they convert a quantity expressed in 1 unit to a quantity expressed in another unit. For example, if we want to convert 5 inches to centimeters, then multiply the given quantity by suitable conversion factor, retaining the units of the physical quantity and that of the conversion factor. Cancel out all the units, leaving behind only the required units. This means that numerator should have that part which is required in the desired result. Thus, 5 inches is equal to 5 inches multiplied by 2.54 centimeters by 1 inch. Thus, 5 inches is equal to 12.70 centimeters. Also note that if the conversion involves many steps, then the conversion factors are selected in such a way that the units of the preceding factor are cancelled out. Let's see an example. Let's say that we have to find the number of seconds in 3 days. We know that 1 day is equal to 24 hours. So we write the conversion factor as shown. We also know that 1 hour is equal to 60 minutes and 1 minute is equal to 60 seconds. In this calculation, we want the answer in seconds. Hence, we will select the conversion factors in such a way that the units of the preceding factor are cancelled out. Thus, in this equation, hours, minutes, and days are cancelled out, and we obtain the answer in seconds.